Welcome to video 10 in our series on quantum computing. In earlier episodes, we explored concrete applications, portfolio optimization with QAOA, option pricing using quantum Monte Carlo, and quantum machine learning for fraud detection. Today, we take a step back and look at the bigger picture, the quantum roadmap. We'll start with why quantum computing matters, the disruptive risk of Q-Day, and what's possible with today's 200 qubit systems. Then we'll look ahead, how the technology may scale, how companies can align their corporate roadmaps, and which adoption strategies make sense. And finally, I'll share my recommendation for how most organizations should prepare, the Strategic Business Explorer. So, is it too early to act or just right? Let's find out. So, why does quantum matter for us? Let's look at it from 4 angles. First, industry impact. In finance, quantum could change how we optimize portfolios, price complex options, or detect fraud. And it doesn't stop there. Pharma and biotech could see breakthroughs in drug discovery, chemicals in materials design, and later we'll see logistics and energy reshaped as well. Entire sectors will feel this wave. Next, security and compliance. One of the most immediate risks is encryption. Today's methods won't survive once powerful quantum computers arrive. That means confidential data is already today at risk through what's called harvest now, decrypt later. Acting early is the only way to protect sensitive information, avoid heavy fines, which could be as high as 10% of annual turnover, and even more importantly, maintain client trust. Then, strategic advantage. Here the story is simple. Moving early pays off. Companies that explore quantum now will be the first to benefit from optimization, risk modeling, and new simulations. And they may also gain new business opportunities by offering quantum services to latecomers in the market. Those who wait may face higher costs to catch up or miss opportunities altogether. Entirely new business models are likely to emerge, and the early adopters will be the ones shaping them. Finally, talent and innovation. Quantum experts are extremely rare. Fewer than 5,000 focus on algorithms globally, compared to more than 500,000 AI specialists. Right now, they're not yet as expensive as AI stars, but they're already in high demand. Attracting and keeping this talent is a signal of leadership inside the organization and out in the wider ecosystem. So taken together, quantum is not just about technology, it's about industry impact, security, competitive advantage, risk mitigation, both regulatory and market side, and the ability to attract the right people. That's why it matters now. Quantum computers can solve many specific problems much better than classical computers. For other problems, they may not provide an advantage. The more an industry depends on problems in the sweet spot of quantum computing, the greater the impact. Therefore, the impact of quantum will not be uniform across industries. Some will be disrupted quickly, others more gradually. Cybersecurity is first in line. Quantum computers will break RSA and ECC and force a move to post-quantum cryptography. That is disruptive and near-term, starting today. In science, pharma, biotech, advanced materials, quantum simulations promise breakthroughs in drug discovery, catalysts, and batteries. The impact is very high, though longer term. For finance and banking, the impact is probably high. Capital markets run on Monte Carlo simulations, risk aggregation, and portfolio optimization, all areas where quantum algorithms can deliver faster, deeper insights. Insurance, hedging, and pricing models will evolve as soon as quantum tools scale. Firms that delay may fall behind in efficiency, risk control, and client trust. Other industries like energy, logistics, and manufacturing will also see gradual but meaningful gains through better optimization, while everyday services such as restaurants or personal care are largely unaffected. So the takeaway: quantum disruption is immediate in security, transformative in science, and strategically relevant in finance. That covers the broader industry impact. But beyond use cases, there's one specific risk that every organization must understand: the threat to our digital security. This is where the concept of Q-Day comes in. So, what exactly is Q-Day? It's the moment when a quantum computer becomes powerful enough to break RSA or ECC, the cryptographic methods that secure almost everything we do online. At that point, confidentiality and authentication systems built on public key cryptography collapse. And there's a second dimension: retroactive risk. Data being intercepted and stored today can be decrypted later. This is what's called harvest now, decrypt later. It means sensitive information already in the hands of adversaries may suddenly become readable once Q-Day arrives. Why is this so relevant? Because public key cryptography underpins nearly all of digital life: personal communication, your email, WhatsApp, and messaging; web security, browser sessions, logins and passwords; payments, credit card data and online transactions; privacy and health records; corporate confidentiality, from client IDs to contracts and strategies; and even cryptocurrencies and digital assets. Their wallets and signatures are based on these same algorithms. If current encryption is broken, these pillars collapse. That's why Q-Day is a systemic risk, not just for banks and governments, but for all of digital society. The good news: post-quantum cryptography, or PQC, has been developed and currently being standardized. And unlike RSA or ECC, it cannot be decrypted by quantum computers. The challenge is making the transition early enough, way before Q-Day arrives. What are the key ingredients for Q-Day? To break RSA 2048 with Shor's algorithm, we'd need roughly 1,700 to 4,000 logical qubits, the stable, error-corrected units built from many noisy physical qubits. With today's overheads, that means somewhere between 170,000 and 20 million physical qubits, plus much lower error rates, longer coherence times, and efficient T-state distillation. We'll take a closer look at logical versus physical qubits in a moment. What do the experts say about timing? The MIT Quantum Index projects a window in the mid to late 2030s, depending on progress in error correction. McKinsey's Quantum Monitor points to a broader range from the early 2030s up to 2040. The consensus is clear. It's not a question of if, but when, and preparation takes years. And we have to remember the harvest now, decrypt later risk. Encrypted data intercepted today can be stored and decrypted once quantum computers are strong enough. That means sensitive communications, contracts, and client data are already today exposed with a time lag of a few years. So the bottom line: Q-Day is unlikely before 2030, but plausibly between 2032 and 2040. Preparation must begin now, because data is already being harvested. Q-Day is the longer-term impact, but what about today? Where do we actually stand with real machines in the cloud? Let's take a quick look at the current quantum computing as a service landscape, what's available, and which platforms lead in qubit count. Major platforms like Azure, IBM, Amazon Bracket, and independent providers give us access to real hardware in the cloud. Devices span superconducting, trapped ion, neutral atom, and photonic technologies. The numbers range from a few dozen qubits up to just over 150 in IBM's superconducting systems. The important takeaway: in autumn 2025, IBM offers the largest gate-based system with 156 qubits. Others, like IonQ, Quantinuum, and Rigetti, are also steadily scaling, each with 20 to 80 qubits accessible today. Neutral atom and photonic systems, such as Quera's Aquila with 256 atoms, or Xanadu's Borealis with 216 modes, are powerful but currently run in analog or special purpose modes, not fully programmable gate-based models. We will look at this in a moment. So in short, gate-based quantum computing as a service offerings are now in the 100 plus qubit range, accessible via the cloud. It's not enough for breaking cryptography, but it is enough to start meaningful experiments and proofs of concept today. Now, before we project into the future, we need to clear up two common misconceptions. Not all quantum computers are the same, and not all qubits are equal. Understanding these two basics is key to judging progress. As we saw on the previous quantum computing as a service table, are two main types of quantum computers today. Annulars and analog devices like D-Wave are designed for very specific optimization problems. They're valuable for very special tasks, but not universal. Gate-based quantum computers like those from IBM, IonQ, Google, or Quantinuum are fully programmable. They can, in principle, run any quantum algorithm. Only these gate-based systems have the potential to transform entire industries. Always be clear which type of quantum computer we are talking about. Analog machines often show larger qubit counts today, but they cannot run arbitrary algorithms. Only gate-based systems are fully programmable. And the second misconception, the raw number of qubits is not the whole story. To measure progress in quantum computing, we need to look beyond the raw number of qubits, and saying just qubits implicitly means physical qubits. What really matters are three things in combination: the number of physical qubits, their quality, and the error correction overhead needed to turn them into reliable logical qubits. Physical qubits are the building blocks, but they're noisy. Their fidelity, coherence time, and crosstalk determine how many of them are needed to create one stable logical qubit. Error correction and state distillation add heavy overhead, often hundreds or thousands of physical qubits for just a single logical one. That's why, while we see 150 or 200 qubit systems today, the real power lies far further ahead. For example, breaking RSA 2048 with Shor's algorithm would require on the order of 2,000 to 4,000 logical qubits. With today's overheads, that translates into hundreds of thousands to tens of millions of physical qubits. So the headline is, physical qubit counts are improving, but logical qubits are the real currency of quantum readiness. So if logical qubits are still years away, what can we actually do with today's noisy 100 to 200 qubit systems? Quite a lot, provided we keep the problem small, the circuits shallow, and combine quantum with classical techniques. Let's look at what's already possible. First, quantum machine learning. This is where today's systems fit best. With variational circuits and quantum neural networks, we can already tackle classification problems, like fraud detection or customer churn, using a few dozen qubits and shallow entangling layers. Generative models and quantum kernels also work in this regime, because the circuits are short, and most of the heavy lifting is done by a classical optimizer. That tolerance for noise makes QML an excellent fit for today's hardware. Second, small optimization problems. With shallow QAOA circuits, say depth 1 to 3, you can experiment with around 20 to 100 variables. That's enough for toy portfolio optimizations, routing subproblems or max cut instances. Warm starts and classical post-processing enhance the results, so even limited quantum runs add value. Third, small-scale simulation. Current devices can simulate toy physics models like Ising or Hubbard Hamiltonians, or run variational chemistry on only very small molecules. The key point is that these small cases are verifiable against exact methods, which makes them useful for benchmarking hardware and compilers. And finally, error correction building blocks. With today's machines, you can already demonstrate basic repetition codes or small surface code tiles. These don't make the machine fault-tolerant yet, but they teach valuable hands-on skills in stabilizers, syndrome extraction, and real-time error suppression. So the takeaway, 100 to 200 qubits aren't enough for breaking cryptography, but they're more than enough to run meaningful proof of concepts, benchmark hardware, and build organizational know-how today. So, with today's 100 to 200 qubit systems, we can already experiment small-scale QML, toy optimization, early simulations, even error correction demos. But these are still limited, noisy, and short-lived runs. The natural next question is, how might this evolve over the next 15 years as machines scale from hundreds of physical qubits to millions? Let's look at a conservative technology roadmap focused on commercially available systems. This chart shows the journey from today's machines to the scale needed for Q-Day. Right now, in 2025, commercially available quantum computers give us around 200 physical qubits, enough for proofs of concept in quantum machine learning, small optimization, and toy simulations. Looking ahead to 2030, we may see systems in the range of 10,000s of physical qubits. That's when the first logical qubits emerge, and with them, more advanced algorithms like amplitude estimation become feasible. By the mid-2030-50s, we cross into the 100,000s of physical qubits. At that stage, depending on progress in error correction, Q-Day becomes a possibility, in an aggressive case even earlier. By the late 2030s, with millions of qubits, Q-Day moves firmly into range, and with it broad disruption across industries. The important point: this is a conservative projection based on published industry roadmaps. Progress must be reassessed regularly, but the direction is clear, from hundreds of qubits today to millions within 15 years, with Q-Day a real risk along the way. This chart gave us the big picture, from hundreds of qubits today to millions by the late 2030s, with Q-Day somewhere in between. Now let's zoom in. This table shows what those milestones actually mean in practice, what you can do at each stage, and how the technology may translate into business use cases. In the near term, 2025 to 2028, we remain in the hundreds to a few thousand physical qubits. That translates into only a handful of logical qubits. Still, it's enough for meaningful pilots, QML on structured data, shallow QAOA optimizations, toy physics models, and first steps in error correction. The focus here is learning and capability building. By the end of the decade, 2029 to 2032, we start to see tens of thousands of qubits and tens to hundreds of logical qubits. That's when amplitude estimation pilots, larger chemistry fragments, and more complex optimizations become feasible. This is where early industry advantage is likely to appear. Moving into the mid-2030s and beyond, the logical qubit counts climb into the thousands. This is where Q-Day risk becomes realistic, cryptography faces pressure, and industries can leverage quantum for production-grade chemistry, optimization, and simulation. The key message of this table is not to debate the numbers, but to understand the progression. From pilots today, to first logical advantage around the end of the decade, to systemic disruption later on. And because the evolution of quantum hardware is highly volatile, this projection should be revisited regularly as error correction and system scale progress. So far, we've seen the technology roadmap, how quantum hardware may evolve over the next 15 years. But for a company, qubit counts don't matter in isolation. What matters is how these technical milestones translate into business actions. That's where the corporate roadmap comes in. In the first phase, 2025 to 2026, quantum is still at the awareness and pilot stage. With only a few hundred qubits available, the focus is on identifying potential business impact, running small proofs of concept, and preparing for post-quantum cryptography. Resource needs are modest, a small innovation budget, cloud subscriptions, and maybe one or two quantum experts supported by IT and legal. By 2027 to 2028, systems scale into the thousands of qubits. That enables broader proof of concepts in finance, such as portfolio optimization or risk modeling, and requires more structured teams, 3 to 5 specialists, stronger vendor partnerships, and closer integration with IT security as PQC migration planning starts. From 2029 to 2032, the company moves into early advantage. Logical qubits begin to appear, allowing production pilots for small workloads, and PQC must be implemented for critical systems. Here we see dedicated R&D budgets, DevOps integration, and larger security and compliance involvement. By the early 2030s, quantum governance becomes part of corporate structure. As we reach 2033 and beyond, quantum shifts from experimental to strategic. By then, post-quantum cryptography must be fully deployed. Quantum workloads become part of business as usual, and new business lines start to open. Larger teams, major infrastructure, and even joint ventures may be required. Finally, by the late 2030s, quantum computing becomes a core capability. Organizations not only defend against Q-Day, but also monetize quantum know-how and establish themselves as industry leaders. The key message of this roadmap is that preparation is staged. Each technical milestone has a matching corporate action, and missing one phase makes the next far more difficult. Okay, now we have a first impression of how important quantum could become for companies, enough to justify serious management attention. Based on my discussions with executives and specialists, I see 3 main adoption approaches today, plus one that I would recommend going forward. The first group are the early adopters. These companies have already set up internal quantum competence centers, sometimes even joint ventures with hardware providers. They believe quantum will bring them competitive advantage, and they want to be ahead of the pack. The upside is clear: first mover learning, strong talent attraction, and a pipeline of intellectual property and options. But there are risks too. Budgets can be burned quickly, credibility can be damaged if promises run ahead of results, and vendor lock-in is a real danger at this stage. The second group are the IT delegated explorers. They usually run 1 or 2 short proofs of concept inside the IT department, often with external specialists. This keeps the cost low and provides quick exposure, but these projects tend to remain tactical. IT departments are already stretched. Their priority is AI and operations, and once the external experts leave, most of the quantum competence leaves with them. The result: little integration into strategy and limited long-term impact. Then there are the lean laggards, those who ignore quantum completely for now. Of course, that means zero cost and complexity today, but it also leaves them unprepared for post-quantum cryptography, late to opportunities, and facing higher transition risks later. The interesting point, though, is that laggards also form a future market. Companies that act earlier and build expertise now will be able to offer services and solutions to these laggards later on, creating entirely new business opportunities across sectors. And this brings me to the fourth way, what I call the strategic business explorer. This is a middle path between heavy early adoption and doing almost nothing. The idea is to set up a lean central team, 1 to 3 full-time equivalents, that works cross-functionally with the business. Their role is to keep an agile technology radar, separating real progress from hype, to run hands-on quantum computing as a service trials, to oversee post-quantum cryptography readiness, and to maintain active exchanges with partners and academia. Importantly, this team speaks in plain business language. reports with evidence first, and avoids vendor lock-in. The strengths of this approach are balance and credibility. You keep costs lean, but you learn early. You detect signals before the market shifts. You build internal leadership and crypto agility without overhyping. The risks are manageable. A small team can be bandwidth constrained and will rely on external partners for deep dives. But overall, the Strategic Business Explorer is the most effective way for most companies to prepare today. It builds knowledge, keeps options open, and positions you not only to protect yourself against Q-Day, but also to capture the opportunities when laggards finally enter the market. So that's the quantum roadmap from a corporate perspective. The message is simple. Start small, stay strategic, and build capabilities, step by step. If you'd like to dive deeper, you'll find more videos on practical quantum use cases, from portfolio optimization to option pricing to machine learning, on qubit-lab.ch. And if you'd like to discuss how this applies to your own organization, feel free to reach out. Thanks for watching, and see you in the next video.